So this is any help you might need with understanding stereoisomerism in transition metal complexes. So this is what the OCR A syllabus states you have to do for this topic of F325. So you have to be able to describe types of stereoisomerism, including those associated with bidentate and multidentate ligands. You need to talk about these being the two types of stereoisomerism you need to know, so cis-trans isomerism and optical isomerism. You need to be able to describe the use also of cis-platin as an anti-cancer drug. So the first thing is, what is stereoisomerism? So you will have come across this term before in F324. It's defined as a species with the same structural formula, but a different arrangement of atoms in space. So these come in two types, as I previously discussed: cis-trans isomers, which we're going to talk about, and optical isomers. Just understand those at this moment as being two types of stereoisomerism. And please make sure you've read this spread if you have the standard OCR textbook, and therefore you'll know what I mean when I'm talking about coordination numbers and this idea of ligands and how they can bond both mono, bi, and multidentate. So the first thing is cis-trans isomerism. Now you don't need to know loads about this or optical isomerism, but this is something you should be aware of. So cis-isomerism is when basically your ligands attached to your central metal ions are together. So if we just use a simple example where we have NiNH3 Cl2, we can see here that our NH3s are together and our Cls are together. If they were opposite, so if you had an NH3 here and NH3 here, as we do here, it's trans because they are opposite to each other. The two ligands are opposite. And it doesn't matter what your coordination number is, so it doesn't matter how many ligands you have giving dative covalent bonds to this central transition metal ion. So you can see here we've got an octahedral shape where we have 6 dative covalent bonds, but this can still be together. As you can see, the NH3s are together, the Cls are together, sort of as close as they can be, that is to say. They're basically just not opposite, whereas here we can look and we can see, okay, we've got a Cl here and a Cl here, so they must be opposite. Again, the NH3s are opposite, this NH3s are opposite. Now this is a bidentate ligand, with the chromium being the central metal ion. Now the same thing applies. Here we have our two H2O ligands together, so it's cis, and here we have them opposite, so we have an we have an O here and an O here, and an O here and an O here. They are together. Here we can see our O's are opposite, yeah, and our H2Os are also opposite, so this must be trans. So a lot of people get confused with when is it a square planar and when is it tetrahedral. Now as you can see in both cases here, this is just a general formula or general structure being shown. We're not using specific ligands or central metal ions at the moment. We can see that the coordination number in both cases is 4. That is to say, we have 4 dative covalent bonds as shown by these wedges. Now you can see the difference just in the shape. This appears, if you were going to draw a box around it, to have 1 in every corner of that box, and here, if you were to draw it here, it looks more like a pyramid with a sort of antenna at the top. Now that's not always useful to you. What will be useful though is understanding the bond angle. So here we have, in a square planar, a 90-degree bond angle. That's the same as an octahedral complex. So basically a square planar is something which acts like it's octahedral, but is just missing these 2 vertical bonds that an octahedral complex would have. So there are only really 2 things they can ask you. So they could ask you to draw a complex ion, to draw the ionic complex, and they could and the information you'd need to know for that was the formula and the bond angle, because you can see here that you have a dative 4 dative covalent bonds, so your coordination number will also be 4, but there's this peculiar thing where it's 90 degrees instead of 109.5. So that gives you the indication that, okay, I'm going to have to draw this one as a square planar. The other thing they might do is tell you that it is a square planar and then expect you to know what the bond angle is in a square planar, so you'd have to know that that was 90 degrees. You might also have to write the formula, but that's not necessarily having to know whether it's tetrahedral or square planar. They are basically the same in terms of the coordination number, but only differ by bond angle and the way in fact you draw it, and they would give you that information. The only square planar you would have to know we will come on to later. Optical isomerism. Now this is the more complicated of the two versions of stereoisomers you need to know. An optical isomer are non-superimposable images of each other. That basically just means they can't place on top of each other. They can't be placed on top of each other. It's like saying try to put your right hand on top of your left hand. If you just try it at home, it doesn't matter how you rotate your right hand, it will never go. It will never fit or superimpose on top of your left hand. So, and if you were to put your hands both flat on the desk in front of you, you can see that they're basically mirror images of each other. And that's exactly what an optical isomer is. So here, this is an example specific to ionic complexes, as you see here. But it sort of gives you that idea. So if you're going to draw this, imagine this was a mirror line. It's sort of like drawing the two complexes to mirror each other. It doesn't matter how you rotate this, it's never going to be able to fit over this one. And the same with here. If we imagine there was a mirror line down here, we would expect, if we imagine there's a mirror line down here, we can see that they're sort of reflections of each other. Again, although it looks much more complicated, you will never be able to fit these two over each other. So that, therefore, they are optical isomers. These can't be stereoisomers because all the dative covalent bonds come from the same atom. So it doesn't matter. They're always going to be together and opposite simultaneously, because N here is next to an NH2, and you've got your NH2 here is opposite an NH2. So it can only exist as an optical isomer. And you don't need to know too much about why, but they rotate plane polarized light. Obviously they have a different shape, and so when light, which travels in all directions, passes through it, it will sort of be filtered into one orientation. Now as they're mirror images, those orientations are going to change. So you might have it going vertically through this one. However, you might have it going horizontally through this one. So the last thing is cis-platin. So all you need to know about cis-platin is that it's a drug used in cancer treatment. So cancer's when cells don't stop dividing. It's this uncontrolled cell division which basically leads to too many cells filling an area, and that's why they're sort of tumours and bulges. So in order for this cell division to happen, DNA needs to be replicated. Okay, what cis-platin is able to do, as you can see up here, is actually bind with that DNA. This changes its structure, meaning it's inactive and it can't replicate itself. Therefore, no more division can take place, and cancer also can't take place. Now, the reason it's cis-platin and not trans-platin, so trans-platin would have an NH here and an NH3 here, and a Cl here and a Cl here, is because we can see the way it's actually bonded. It needs, the two Cls need to be kind of together in order to bond. If you had one Cl here and one Cl here, it would be too far apart for them actually to alter DNA correctly. And that's all you need to know on stereoisomerism. So have we met these criteria? So we've described the types of stereoisomerism showed by complexes, yes, because we know we've got cis-trans and we know cis is together and trans is opposite. And we have optical isomerism, which basically means that it's a mirror image and that those two can't therefore be placed over each other. We know what effect that has on light too. So yes, I think we have met these criteria. So now Can we describe the use of cis-platin as an anti-cancer drug? So that's just describing how it works, and it actually gives you this bit of advantage in this specification where it says specifically what you need to know about it being an anti-cancer drug. So we do know, of course, that it binds to DNA and how that prevents division by changing the shape of DNA. And that is it. So thank you guys.